right. So we're going to jump in and we're going to talk about, as you can see, there are a bunch of reactions on here. But we're going to start here with reactions of alcohols. And we're going to pick up just the first reaction, the transesterification. We'll talk about that. And then we'll get down to, this also would classify as a reaction of alcohol, but we get down to here, conversions of alcohols into carbonyls. All of this stuff is basically the same, right? We're not going to go through any mechanisms for these reactions. So all the oxidations we can discuss because they all do the same thing. And then over here, we're going to do the Wittig reaction. And then down here, we're going to do imine synthesis. Because amide formation and ester formation work the same way, so we won't have to necessarily go through the mechanism for that. But we'll do imine synthesis or imine formation. All right, so the first reaction that we're going to look at is up top, right here, transesterification. Right, you've done this before. You just may not have realized that you were doing it when we did the aspirin reaction and we converted aspirin into converted salicylic acid into aspirin. That was an example of a esterification, right? Because, well, it was a type of esterification, right? Because we took the OH group on the aspirin. Let me just draw it down here. We took salicylic acid, which is this. Oh, great. And then we reacted that with acetic anhydride, and we ended up with the ester. Right, where the alcohol is on salicylic acid, so we ended up with this. So that's an example of an esterification. It's not a transesterification, but it's an example of one. So for esterification, and the key to all this stuff is going to be to remember your functional groups. You're taking I'm going to start with a basic, I'm going to start with benzoic acid. So with transesterification, we're starting with a carboxylic acid. I'm going to use benzoic acid. All right, we're treating it with an alcohol. I'm going to use methanol. We do it in the presence of a catalyst, acid catalyst, some kind of weak acid, maybe HCl or acetic acid or something like that. My plus sign is still terrible. Right, so some type of acid catalyst that's going to activate your carbonyl and then heat it up. Right, and so the outcome of that reaction is this. And then we're going to go back and explain how it happens.
Dr. Russell, the file for the final reactions worksheet, it's like really like blurry and kind of like upside down almost.
The one in Blackboard?
Yeah, the second we just uploaded, the one that says final reactions worksheet.
Yeah.
Yeah, it's like upside down. Half of it is, and the other side's like blurry, like real bad.
I wonder why that is. That's the same thing I just emailed to myself.
Yeah, because it looks on your screen, but then I just opened it. It was like, oh man.
It may be something going on with Blackboard. I can
Mine looks fine.
So has anyone else opened it? Is it jacked up?
Yeah, mine is fine. It's not missing.
Mine looks fine.
It might be something you might want to download it instead of opening it. Just download it, save it, and then open it with Adobe. That may help. All right. So again, we've taken a carboxylic acid, and we've converted it to an ester, right? You can see the difference in the functional groups, right? We took, and this is a really basic explanation of this. We swapped the OH group out with the methoxy group. You can see that over here. And then the side product obviously is water. That's all right. Right, because you took basically this H right here and the OH right here. That's where your water is going to come from. All right. So let's talk about how this works. And again, everything that we talk about in this section is going to hinge on two things for you to understand. One is functional groups, like what they are. When you hear the name ester, what do you think? When you hear the name aldehyde, ketone, so on and so forth. The other is nucleophiles and electrophiles. Like if that's not clear at this point, yeah, this is gonna seem like Chinese, right? No offense to anybody that's Chinese. That's a hard language to learn. All right, so let's look at how it works. All right, I can leave that. So obviously your alcohol here has an oxygen with lone pairs. So in this case, this is going to be your nucleophile, right? All carbonyls are electrophiles. Why can I not write plus signs today? All carbonyls are electrophiles, right? That's because what? Somebody help me. Tell me why every carbonyl is an electrophile.
There's a dipole going towards oxygen. So
big giant dipole, right?
Carbon partially positive.
Yeah, so carbon is partially positive. And if you do resonance and put the pi electrons on oxygen, carbon will be fully positive. So every carbonyl is an electrophile. So just like we learned in part one, nucleophiles attack electrophiles. But when you attack an electrophile like a carbonyl, what you end up doing is having to break that pi bond, right? So those electrons in the pi bond end up being given to oxygen. Let me put these up here too, because it already has two lone pairs, right? And so once you do that, you get an intermediate, right? So I'm gonna draw that down here. So let me switch back to blue. So here's my intermediate. This is that doesn't change. This part is gonna change because now that's O negative, right? And then you have the OH here, and then the OCH3H here. So now that's positive, right? Any questions about that? This intermediate, anytime you add to a carbonyl, you're gonna get this type of tetrahedral intermediate. Right? That's going to be a common intermediate for every carbonyl addition. Not this one in particular, but every carbonyl addition is going to go through a tetrahedral intermediate before going to product. All right. Now from this intermediate, let me do this too right quick. Make this a little clearer. From this intermediate, I want to lose water. How could I make water from this intermediate?
Would you take a pair of electrons off the oxygen negative and like do resonance or?
But I already have an OH group right here, don't I? All I need to do is add one more H to it to get rid of it. Is that right? Or to make it into water.
Yeah.
Could I do that? And do I have a H that I can give to it to turn it into water?
Would you break the bond on the H down here?
I got a hydrogen right here.
Yeah.
Mm-hmm. So I can just do what's that called when we do pick up a proton?
Hydrogen ship? No.
A hydrogen ship, you're moving a hydrogen with electrons. I heard somebody say it. I think it was Jalen.
You said it's not the hydrogen ship?
It's not a hydrogen ship. It's a proton transfer.
Oh. That makes sense. Yeah.
Right, that's moving H plus. Hydrogen ship is moving H minus, right?
Yeah.
Yeah. So let me erase that, because when you go back and watch this, you're gonna be asking about the H minus. Where did that come from? Right. So we just want to move H plus. So we can do that by this oxygen pulling off that proton and then giving that pair of electrons to this oxygen. So that will result in another intermediate, which is going to look like this. That's O minus, that's O. And then this is OCH3. Yes or no?
Okay, then would you move the electrons off the oxygen negative?
So now we can force that water out. Right now we can force it out. Right. And that's going to give me my ester plus water. So that's a type of condensation. All right, let me ask a question. What type of reaction is this overall? Like, what did I do in the first step?
Substitution.
Is it a substitution? It kind of looks like that. But if you remember when we talked about substitution and elimination and addition and rearrangement, you can't substitute on a carbon that's sp2 hybridized.
Addition?
Yeah, it's an addition. It's an addition followed by what? So the first step is addition. I agree with that. That's good. So this part is this is an addition. And then how do we know it's an addition? Because we took a pi bond and we added something to it, right? And that pi bond got broken. Additions happen on pi bonds, whether it be a triple or a double bond. And then down here, what is this step to give me? Let me draw the ester out so you can see the product.
That's the elimination.
It'll be elimination, right? So anytime you add to you do an esterification, right? It's an addition followed by an elimination. And you can tell you did elimination because you create a pi bond in the product. So if you add to a pi bond and break it, that's an addition. If you make a pi bond, that's an elimination.
Can you scroll back down a little bit?
Say again?
Scroll back down a little bit.
How about that?
Yep.
Is that better?
Thank you.
Mm-hmm. So let me erase the condensation part now, because I don't